Hi, everybody. We're just gonna wait a few more minutes just for other people to get into the classroom. Since you're waiting, I'm just curious, are your teachers letting you do live lessons at school, or are they like preventing you from doing that?
Like all my teachers have been doing is sending us like 2 FRQs a day as review.
And are they grading them?
Is he grading them?
Yeah.
Yeah. But they're just like past AP FRQs, that's it. Like it's been left up to us to like study for it actually.
I see. All right, we have a few people in here, so I'm gonna get started then. So today we're gonna cover everything and anything related to just the basic function of taking an antiderivative or taking an integral. We've done basically all of differentiation already, so we will be applying the reverse operation today. And, oh, where the heck did I put it? I might have to go find my pop quiz. Where did I put my pop quiz? Give me a second to get my pop quiz. I can't not have a pop quiz today. There it is. Okay. Zoom out so you can see it. And then, so there's just a couple questions. Remember, it's going to be all about justifying your answers. So I have 2 questions for the pop quiz today. If you're being asked for a relative minimum, which of the following 6 would be acceptable justifications for a relative minimum? Could you do a number line test? Could you say any of the following? Or choose the answers that you think are right. And I'm just going to make up a random number line for this. Plus, minus, plus, plus. Which of these would the AP readers award you a point for a relative minimum? And then question number 2 is, which of the following would the AP readers award you credit for if they asked you for an absolute minimum? So we can do a similar number line test there. Put some random numbers. Like I've said many times, I'm guessing that there's going to be a lot of justification on the exam this year. Just because that's a little bit harder to cheat on. And remember, you can pick multiple ones too. So there's not one proper justification for any of these, or maybe there is, I don't know. Share with you in a second. I'll give you a few more seconds to get in your answer. Five, four, three, two, one. Okay. So I did this kind of as a, I don't know if it's a trick or not, but I mean, a number line test is not justifiable for either type of question. So you can use a number line test to help you, but they will not award you any credit for drawing a number line anywhere on your tests. Okay, so for the first one, if you're trying to establish a relative minimum, you could say something like along the lines of number 2, and you could say something along the lines of number 5, and you could also say something along the lines of number 6. So pay attention to the wording here. Q changes from decreasing to increasing. That is an acceptable definition of a relative minimum, assuming that the function is continuous. Number 5, it says Q prime, so the slope changes from negative to positive. That's basically what the number line test is saying, but number 5 is saying it in actual words. And then number 6 is the second derivative justification. So if you've shown that there's a critical value at that point, and you know that your second derivative is negative, AKA concave down, ooh, that's a maximum. I should have said concave, we want concave up. I should have had that, so I'm glad, well, one of you chose it. If a function is concave up, and you know there's a critical value, then that's a absolute minimum. Or not absolute, excuse me, relative minimum. And then for part 2, again, we can't use a number line test. I kind of threw in number 2 to trick you. You can't just plug in your critical values when you're doing an absolute minimum. You have to do your critical values and endpoints today and show that R4 is the smallest. And then number 4 is also possible. It's just a more complicated way of showing that something's a relative min. If you know that something is concave down, oh, this should have said concave up again. I messed up this test. As something is concave up on the entire interval, then you know that it should be a absolute min. Any questions on that? Okay. So let's move on to some of our derivative stuff today. We're going to start off by talking about antiderivatives, right? So a function f is an antiderivative of f on the interval if f prime of x is equal to f of x. And what's the big deal about antiderivatives? People forget that when you take an antiderivative, you need a plus c term somewhere, right? Because all of these, if we were to take the derivative of these, would equal x squared. So as a quick review, if we want to do the general antiderivative of a function that's timed by c, does anybody know what the answer for that one might be? Assuming that, let's assume that capital F is the antiderivative of little f. If we were to take the antiderivative of a function with a constant in front, it'd be c times the antiderivative. Right, you can just take times the antiderivative function and then plus the big constant c. Number 2, what happens when you add or subtract functions? Well, when you take the antiderivative, it's just going to be the same exact thing. You can add or subtract the antiderivative functions. What about here, the power rule? Who can tell me what to do with the power rule? So you can raise the power by 1, right? So it's x to the n plus 1, all of which over n plus 1, right, plus the c. I'm just going to keep hammering home. Oop, I even forgot a c here. Do not forget your constant there. They will literally dock you a point. And when you're only getting like 9 points on a test, 1 point is a lot. What about 1 over x? ln x, good. ln x plus c. And don't forget, this one's absolute value of x. I don't think they're going to dock you for it. Absolute value of x plus c. E to the x, that's the one that never changes, right? And then this one, please have this one out because people forget the signs here. The antiderivative of cosine x is sine of x. The antiderivative of sine of x is negative cosine of x. Don't forget the tans are sexy. And I guess cosecants, cotans are cosexy maybe? I don't know. Secant tangent, if you know your derivative rules, then you should know your antiderivative rules. This will be negative cosecant x. Who remembers these ones, the last 3? Which one's which? Arcsine, arctan. Yes, the first one is arcsine. The second one is arctan. I'm going to write arctan slightly differently just to remind you, you can write it that way. The last one is arcsecant. Okay, arcsine, arctan, arcsecant. So if you want to have a little derivative table or integral table, that's great. I really don't think you'll need one, but who knows? All right. So the other thing is you just need to know certain antiderivative techniques of integration, because sometimes you know how to do the simple ones, but then you get and you look at something and then it becomes impossible to antiderive. So for example, does anybody know what we should do for letter A? Because it looks really, really gnarly right now. Feel free to type, or you can also use voice if you'd like. I see somebody said U substitution, and maybe, but actually that's probably not going to be helpful here. I will be doing U substitution later though. Try to factor out the constants, absolutely. So if we factor out the constants, we have a 5 on top, right? And then we're also going to convert the top into exponential form, because then you can see something magical is going to happen when we factor out the constant on the bottom. Look at that, it's 1 minus x squared. They have the same base. So this could actually be written as 5 over 3, 1 minus x squared to the negative 1/2 power. Or 5/3, 1 over square root of 1 minus x squared. And hey, what the heck is that? If we were to integrate that, that would be the integral of arc sine of x plus c. And do not forget the 5/3 because the constant stays through. Right, so maybe there's some sort of thing that you can cancel out that's in disguise. What about c? There is no clear antiderivative for tangent squared, at least on the derivative or the integral table. I don't know if you're going to need this, but don't forget that sine squared x plus cosine squared x is equal to 1. Right, so from that, we can also divide everything. If we divide everything by cosine squared of x, what do we get? We get tangent squared x plus 1 is equal to secant squared x, right? And we do know the antiderivative for secant. So we would do a trig substitution there. Not a big deal. I don't think that's going to show up, but E is very likely to show up right here. You could try to do U substitution, you'll get into trouble. So E would be one where you might want to FOIL or distribute everything out first. Okay, so that's E. I'll write distribute here. And then what about F? Look at that for a second and see. is there a way that we can do this without using U substitution? Partial fraction decomposition. Oh my God, if they actually did that on the test. I know that's part of the BC curriculum, but oh. Factoring, yeah, you could factor a long division. Okay, so if we factor the top, right, always try to factor x minus 7, x plus 2, right, all over x minus 7. And so we could just take the derivative of x plus 2 dx. I'm sorry, antiderivative. I should put a dx here. Always remember when you're writing this out, if you're going to handwrite it, make sure you put the integrand sign on one side and the dx on the other, kind of like a brackets or something. We get what, x squared over 2 plus 2x plus c, okay? So this is acceptable except for one little thing here. This antiderivative is not exactly equal because earlier we had x minus 7 in the denominator. So if you were to get a question like this, don't forget to write out x cannot equal 7 and include it in here because we don't want to have that discontinuity be the reason we don't get full credit. Cool. So basically, if you were to get an antiderivative question, make sure you try to do some factoring or simplification to make your life easier before you move on with it. Otherwise, you might get stuck. Any questions there? Okay, let's go on to the next thingy. So you might get antiderivatives, but I think you're more likely going to get definite integrals. So what is a definite integral? You have the bounds in the top and the bottom, right? And the definite integral represents the area under the curve from A to B. And that's only true if the function is non-negative. If the function is negative, then you get a negative answer for your area. So that's something that they like to play around with. So for example, we have this curve over here, right? So the blue line is above the x-axis from -5 to 2, so you're gonna have a positive area, then it dips below, so you get a negative area, and then it goes back above the x-axis, so you have a positive area on the right. Joey asked, do you think by parts will show up on the test? I really don't think by parts will show up. They love these integral questions for both A, B, and BC, so that's why I'm focusing on this. And then the other thing is you can also integrate from right to left. So if you were to integrate from right to left, then basically the signs flip, right? So anything above the x-axis is negative and anything below the x-axis is positive. Or if it helps you make more sense of it, you could also write it this way. If you flip the bounds of your integral, it would be as if you get the negative version of your answer. Another theorem for you to remember. So please make note of this. If a function asks you for the total area under the curve, you need to take the absolute value of your function. If you do not use the absolute value of the function, you'll get the net area or the net accumulation. If you want the total area, make sure to write this notation. Okay. So to give you another little quiz, let me set up the poll right now. I have 5 questions to answer, right? So they give you that A1 and A2 are positive numbers that represent the area of the shaded regions, and find each of them in terms of A1 and A2. So the first one's asking for the area from -4 to -1, then -1 to 4, 4 to -1, -4 to 4, and then we have this gnarly one for part E. First couple are easy, right? I'll let you keep considering E as I start explaining this for other people who are watching. The area from -4 to -1, that's just 1, right? A1. Like this could totally be something that shows up on the test, right? You use letters. You can't plug these letters into a calculator. Part B, it's under the curve, right? So part B is -A2 because they told me at the beginning that A2 was a positive number. Then part C, if we're integrating backwards from 4 to -1, then it flips the sign, right? So you could flip the sign, or you could think that the integral from -4 to -1 is equal to the negative integral from 1 to 4. Two ways of thinking about it. Part D, if you're adding up all the areas, this is not asking for the absolute value, right? So it's 1 plus -A2. There's no absolute value sign around there. All right, and then let me work out part E for all y'all. Part E, we want the total area, which we can steal from part D, right? So that's just gonna be A1 minus A2. And then minus 2, and then we can steal that from part B, right? We know this area from part B is -A2 minus 2, -A2. And then you get A1 minus A2 plus 2A2. Don't forget to distribute the negative. I think that's why that question's there. So the final area of that one would be A1 plus A2. Any questions on those? So please be careful with your distribution. Alrighty, and then here's a table. Again, this is going to be in your Dropbox, so if you want to access that, I'll have this uploaded. And you just need to know all these different properties. If you're integrating from the same bound to the same bound, there is no area, right? We talked about this one where if you switch the bounds around, you get the negative area. For part C, if you factor something out, you just can factor out that constant. You can split up the sum of two different functions and integrate each function separately. If you have a constant in front, you can do that. And then part C, we haven't really, or part 6, we haven't really talked about. If you have an integral along a certain boundary, you can split up the interval into 2 subintervals, and this number here has to match up with this number there. Right? And then you can basically split the area under the curve into 2 separate areas and add them up individually. Okay, so that's going to be a very likely question. So since it's so likely, I'm going to walk you through example number 13. So example number 13 says we're given this area here from 4 to -6. We're given an area from 3 to 7. We're given another area from 4 to 7. And then we want to find the area from -6 to 3. So first things first, I don't like how this one's structured, right? This one's structured where the lower number's on top. So I'm going to rewrite this and put the lower number on bottom, -6 to 4 of f of x dx. Right, that's going to equal 3. And then look here, I see this 4 on top, right? And this 4 links to this 4 over here. So I can add those two areas together, right? So -6 to 4 of f of x dx plus 4 to 7 of f of x dx is going to equal the area from -6 to 7. Right, and what's the area from -6 to 7? It's just 3 plus 5, so that's equal to 8. And then from there, we're trying to find -6 to 3, right? So if we want to find -6 to 3, we can do -6 to 3 of f of x dx. And then what are we given? We're given 3 to 7 up here. The area from 3 to 7 of f of x dx is also equal to 8. Right, so -6 to 3 of f of x dx plus 9 is equal to 8. So then we know that the area of the function between -6 and 3 is -1. Cool, so that's the start to this question. And now we can go ahead and evaluate the gnarly function that they give us. So we'll do a few different rules, right? When you have a constant with the f of x, you can factor out the constant in front of the integrand. And then when you have a sum or a difference, you can split it up into 2 separate integrals. right? And then we know that the area from -6 to 3 is -1. And then if you want to integrate from -6 to 3 of 3, it's just 3 times upper minus lower. So you get -1/2 minus 3 times 9. So that's -27.5. Questions on that? So you could get something like this, or you could get something like this with A's and B's, and then you just have to manipulate a bunch of A's and B's as well. So another thing that you could get on this test is you need to know all your different Riemann sums here. So you could get a table, and then they'll ask you to integrate the area, or approximate the area, excuse me, using 3 equal subintervals. So if we want to use 3 equal subintervals, we can do something like this. This is this, and this is this. And we know that each of our subintervals has a width of 2. So I would expect if you're to get a table on the test, do not assume that your intervals are the same. In this one, they are. And then if we're going to use the right subinterval, then we're going to use this one, right? Because this one's the point on the right out of this one and this one. We're going to use this one, and we're going to use this one. And so how do you answer this? So first of all, you put the symbol, right? Integral from 0 to 6 of f of x dx. And if you can, if you're going to handwrite it, use these approximation symbols, and then they will award you credit if you can show them that you're multiplying something to get a rectangle, right? So we need a base. Our base is 2, and our height is 8.3 for the first one, plus 2 times 2.3 plus 2 times -10.5, right? If you can show that you have the two sides equal and you use your some sort of product and then you add things up, you should get full credit for that one. If we want to use left endpoints, it's literally the same process, except I'm going to use these 3 now, right? So we'll say integral 0 to 6 of f of x dx is approximately equal to 2. And in this case, since the widths are the same, I'll show you a different way of writing it. You could also write it like this. Okay, this would also get full credit, assuming that the width intervals are all the same. We can also do midpoints. Right, if we do our midpoints, then we're going to use the middle values. We're going to use neither endpoint. Oops, don't use equals, use squigglies. 2 times 9.0 plus 6.5 minus 7.6. All right, so those are the straightforward ones. What about the trapezoid one, though? What's the area of a trapezoid? Lita asks, do you have to evaluate? No, that's the nice thing, right? On the test, as long as your numbers are right, you can just leave it like that. So the trapezoidal rule, do not forget that the area of a trapezoid is equal to 1/2 the bases added together, or you could think of that as the average of the bases times the height. And in this case, the height is going to be the width of your subinterval. So in this case, each of your heights is 2. And then we're going to use these as our bases, right? So the heights or the y values will represent each of your bases. So then the integral from 0 to 6 of f of x dx is going to approximately equal 1/2. I'm going to put the 2 for my height, and then I'm going to average my bases. Oh no, the 1/2 stands for the average. So 9.3 plus 8.3 plus 1/2 the width times 8.3 plus 2.3 plus 1/2 the width times 2.3 minus 10.5. Okay, so that's your trapezoidal rule approximation. Out of all of these, which ones do you think is the closest approximation? A, B, C, or D? D, right? The trapezoid. The trapezoid is the most accurate. And then one more question that they could ask you. It says, if the function is said to be decreasing, can you say whether your estimates are less than or equal to the exact value of the integral? Are you over approximating or under approximating if you have a monotonic decreasing function? Let's go for right endpoints. If you have right endpoints, are you over or under approximating? When you have right endpoints and your function is monotonic decreasing, you're actually under approximating, and you can draw out a picture, right? Because your right end rectangles are going to hit and you have all that empty space below the curve. So RER is under. If you have left-hand rectangles and you have a decreasing function, then you have an over approximation. So LER is over. With the other two, with the midpoint and the trapezoid rule, you really, really can't tell, and they're not going to ask you something that complicated. Any questions on that one? Okay. So that's a really quick review of Riemann sum. Let's move on to the fundamental theorem of calculus. You will very likely have to evoke this rule along some point during the test. So this one first, right? If you have f continuous on a to b and f is an antiderivative of f, then you have this. I have a question. What is the answer to, could any of these approximate the area? Let me go back to this really quickly. The question is, could any of these estimates approximate the area of the enclosed region with the x-axis? That's actually the definition of an integral, right? So if you have a graph here, let me zoom in so I can draw a lovely graph, right? And then you have your graph here. And then when you draw your rectangles, what are you bounded by? You're bounded on the bottom by the x-axis. So usually when you get wording on the question, it'll say the area between the curve and the x-axis. And these are all approximations of that area between the curve and the x-axis. Yeah, all of them are approximations. I didn't really focus on the question because if you were to see a question on the test, it would just literally say, find a right end rectangle approximation, and then tell me if it's an overestimate or an underestimate. All right, so back to the fundamental theorem of calculus, right? So this part you've done millions of times in class, I'm guessing, right? You just take the antiderivative, you plug in your upper bound, and you minus your lower bound. But in case you're curious, you could just say fundamental theorem of calculus part 1. And as we said earlier, this gives you the net change, right? If we wanted the total change, we'd have to take the absolute value of the function. So then you could get a question like this on the test, right? It says they give you the graph of f of t and let big F equal the integral from 2 to x. So that means the area starting from 2. So what do y'all think big F of 2 is? Big F of 2 is just 0, right? Because there's a couple ways you can think about it. The area between 2 and 2 is nothing, right? It's negligible. Or you could think of this is equal to f of 2 minus f of 2, right? Using the fundamental theorem of calculus. What about f of 9? What is the area, or what is the value of f of 9? Excuse me. We're going to set that boundary there. We can do this trapezoid right here. All right, what do we have as that base? That's a base of 7. What's the base here? We have 5. All right, what's the height of our trapezoid? 20. Paying attention is the area above the x-axis, right? So we just do 1/2. We average the bases, 5 plus 7, times it by the height. That'd be your answer for part B. Then part C, what do we have to do? We have to remember to subtract this area down here, right? Because that area is beneath the x-axis. And then what do we do for part D? Then we add this other thing over here, right? So B, C, and D are pretty straightforward. And please be careful with part E, right? Part E, if we plug in 0, we're integrating from 2 to 0 of f of t dt, right? So you have two options here. You either find the area and then make it negative, or if you find that confusing, make sure you flip the sign around and put the negative, whoops, and then switch the bounds, and then do it that way so you don't miss out because you forgot the negative sign. Cool. Fundamental theorem of calculus part 2. This one's the most confusing part. Well, it's kind of confusing and it's not confusing. So this one's the easy part, right? If you have the integral from some sort of constant here at the bottom to a variable on top. So we have a constant here. That constant could be 1,000,000 if you wanted it to be. And then you have a variable. Literally what happens, if you take the derivative of an integral, they basically cancel each other out. So these examples are really straightforward then. If you take the integral from any constant of if you take the derivative of an integral with respect to x, you just get secant x. Part B, if you just take it, it's literally just direct substitution. So square root of x cubed, sine of x, and then what? E to the x square root of x plus x squared over ln x. Right, derivative of integral cancel out. A couple things you do want to note. If you were to set up something like this, make sure that the variable in your integral is different from the variable up here. They should not be the same x value, or they should not be p and p. Right, so they'll usually use the letter t, and then they'll put the x in the integral sign. So this one's pretty straightforward. Let's move on to the more complicated version of this. Whoa, what the heck is that saying? So here you're integrating with something a little bit more complicated than just an x in your bounds. So this is basically just saying chain rule. So you could see a question like A. If you were to take the derivative of this integral, it would be as if you're plugging in that t with that upper boundary, right? You're plugging in that upper boundary there. And then since you're taking the derivative, you have to remember to multiply by the derivative of what's on the inside. So this is the answer for part A. We still have that constant on the bottom, right? Versus part B, right? Part B, now we have the function in the bottom. I don't like having the function in the bottom, so I'm going to reverse the order of my boundaries and make my integral negative. Now, if I want to take the derivative of this, I can just go ahead and plug in my upper bound. Right, so it's negative e to the x squared. Oops, put big brackets here because this whole thing is negative. Minus 5 e to the x. And please do not forget your chain rule times the derivative of your upper bound. That's the really quick way of taking the derivative of an integral when you have a complicated function in your integral. Questions on that one? The last thing you're gonna get asked if you have a conceptual integral problem is the mean value theorem. Right, so this is one way of writing the mean value theorem, or you have this way on the bottom that's a little bit more common, right? The average value of a function. Okay. And so when you start getting the word problems, you could think of area under the curve as, or you can think of the integral as area under the curve. You can also think of an integral as the amount you accumulated. So for example, if I were to integrate my rate function f prime of x, this would be the amount accumulated between a and b. But the problem with the accumulation part is that doesn't take into account how much you started with. So that's where a lot of people miss out on a point, is they calculate the integral and get that number, but they forget to plug in your starting value. So let's say you get a question like this, which is very likely. You're given a function and it says raw sewage is leaking from a storage tank at a rate given by that function. And notice that it says that S is given as a rate, where S is measured in gallons per hours. How would you respond to A if you had to like type out your answer? Obviously you could write it out or type it out, but how would you write out your answer without actually calculating it? So we're given the boundaries, right? How much sewage is leaked out between those 2 hours? So we could say take the integral of S of t from 2 to 5, right? You could write something like that as a full sentence. Pay attention to the wording, right? It says how much sewage is leaked out between those 2 hours. So we didn't need to add anything, right? Because that 572 at the beginning, it didn't leak out. It was just sitting there, right? There's 572 gallons leaking out. Right? We start off with 572 gallons. If we just integrate the function, we get how much is leaked out. Now, part B says how much sewage was initially in the tank when it started leaking at 0 hours. So how would you do this one? I think this one would be harder to write out as a sentence, so we could like do this, right? If we want to find how much was initially in the tank, we could do what? The integral from 0 to 2 of S of t dt. So this is the rate function, right? And what is that equal to? This is what? Big S of 2 minus big S of 0. Yeah, and then we want to solve for how much sewage was in the tank, right? We're solving for S of 0. So if we were to rearrange this equation, it'd be S of 0, which is the amount that we're starting with, is equal to big S of 2 minus the integral from 0 to 2 of S of t dt. And then we know that S of 2 is 572, right? So 572 minus the integral from 0 to 2 of S of t dt. And then part C says, write an integral equation that gives the amount of raw sewage in the tank at any time t. So part C is where you want to keep in mind that you started at 572, right? So we had 572. And then here, it says raw sewage is leaking, right? So it's going to be 572 minus the integral from 0 to t of 5 of s of t dt. Oh, sorry, not 572. We need to take our whatever value we got there. I'm trying to do this conceptually without actually doing real numbers, so that's throwing me a bit off. We're taking the number that we got in part B. Any questions on that one? I was being a little bit overly conceptual on that one. I should have picked a better problem. One more idea here, very straightforward, right? If you're given a function about a man gaining weight and it's given as a rate, what was the man's weight at the end of break 14 days later? How would you write this out using a complete sentence? This one you want to figure out the starting value, right? We want the total weight. So the total weight, he starts at 180 plus the integral from 0 to 14 of w prime of t dt, right? You'd write something like that as your answer for your total weight. So keep in mind, when you get a free response question, and if it's dealing with accumulation, you need to be able to separate the idea of amount accumulated versus total value. Last part of integration is doing U substitution. So when you have a linear nested function, it's super easy to do U substitution, right? So if we want to take the integral of this, or antiderivative, instead of multiplying as you do with derivatives, right, I just think about it as dividing. It's just the opposite function, right? So if I were to take the integral of cosine is sine of 3x, right, divided by 3 plus c. So that would be your f prime of x. Please do not forget your plus c. Now, if we want to take the integral again of that, what do we get? The integral of sine is negative cosine. This 9/3 becomes negative 3 cosine of 3x, right? We divide by 3 one more time, the reverse chain rule. When we integrate a c, it becomes cx, right? Any constant integrated takes on an x value, and then you have another constant, so we use d. So my guess is if you had to do U substitution, it'd be something pretty simple like that. Right, same with part 2. Right, if we were to integrate this one, we could split it up, right? So the integral of 1 plus the integral of e to the negative x. Oh, whoops, there's a squared in there. So let's go ahead and FOIL everything out first before I get into trouble. So it's 1 plus 2e to the negative x plus e to the negative x quantity squared. Right, that's your distribution if you're to FOIL it out. And now we can take the integral of each of those components separately, right? So integral of 1 plus the integral of 2e to the negative x plus the integral e to the negative x squared. It can also be written as e to the negative 2x. And then make sure I put in my dx's to complete my brackets around each integral statement, right? The integral of 1 is just x. The integral of 2e to the negative x, it's 2e to the negative x. Since I have a linear function in here, I just divide by the derivative of that. Same thing for the second one, right? E to the negative 2x, and I'm going to divide this one by negative 2. I was doing 3 separate integrals, right? So each, let's pretend it's indefinite, right? So each of these take a different constant, but somehow magically, right, when you add all these unknown constants together, you can just consider it one big constant. So this would be your proper antiderivative if you wanted to do that. Then, of course, we finally get to one where we have to do actual u substitution. So if we're going to take the integral of 6x e to the negative 2x squared dx, right, we should let our u probably equal something that's nested in our function, right? So I'm going to let my u equal that exponent up there, negative 2x squared. Take the derivative of both sides with respect to x. Right, so I get du dx is equal to negative 4x. I can multiply both sides by the dx, so I get du is equal to negative 4x dx. And then move the negative 4x over. This is how I do it. Other people have other methods. Du divided by negative 4x. Now that I've isolated dx, I can go ahead and plug this du over negative 4x into there. I can go ahead and plug my u function into there. So then if I take my integral, it's the integral of 6x e to the u times du over negative 4x. I do that so that I can cancel out my x's, right? You know that you're doing something right if something cancels out. And then what do I get? I get negative 3 over 2. Since it's a constant, I can factor it out of my integral, e to the u du. Integral of e to the u is just e to the u, right? So my answer is 3/2 e to the u plus c. I'm doing antiderivatives right now. And then final step, you can go ahead and plug the u value back in. So negative 3/2 e to the negative 2x squared plus c, right? That would be your antiderivative. So that's a really quick refresher on what u substitution is. And so how would it show up on the test? It could show up on the test like this, right? Instead of having actual numbers to do, you have to take the antiderivative of that really weird nested looking function. What do y'all think I should let my u equal here? I have a vote for ax, ln ax. 1 over x? No, we're gonna use the nested function, right? It's the one on the inside. So we're gonna let our u equal ln of ax. So let's hit both sides with our derivative, right? So we're gonna take both sides, derivative with respect to x. So we get du dx. What does the right-hand side equal? What's the derivative of ln of ax? It's 1 over x, right? So we get, when we take the derivative of this, if you want to think about it, derivative of ln, right, is 1 over the inside, right, times the chain rule. A is a constant, so then we get du dx is equal to 1 over x. If I cross multiply this whole thing, I get x times du is equal to dx. And now I can do my substitution, right? So I have my integral of sine of u times x du over x. Normally, when we're doing our u substitution, we're so used to seeing the thing that we need to substitute be in the numerator, right? ln x is one of the weird situations where the thing that cancels out is in the denominator. That's why I think this is an apropos question. Number one, because it has weird constants in it. And then number two, because it has an x in the denominator. So here you cancel out the x's, right? So you just get the integral of sine of u du. Integral of sine, don't forget, it's negative cosine of u plus c, right? And then last step, we need to plug in the u back in. So it's negative cosine of ln ax plus c. That is a valid question. Any questions there? Another valid question type would be this, because these are all given in terms of letters. Right, so let me show you how I do it, and then I'm gonna set you off on this. So we're given that the area under the curve is equal to k, right? So we're gonna let u equal x minus 5. So if we do that, we have our integral of f of u dx, right? So what do we need to do? We need to take the derivative of both sides, so we get du dx is equal to 1. So we can just say du is equal to dx. The other thing we need to do is, since everything's in terms of x right now, we need to plug this into our boundaries to find our new bounds. So when we plug in our boundaries, b plus 5 minus 5 is just b, right? And a plus 5 minus 5 is just a. So if I were to simplify this, it would just be the area from a to b of f of u du. And now that everything matches up, my area is just equal to k. That one's pretty easy. Okay, part B. When we want to evaluate this integral here, we just have to separate it, right? So we get a, b, f of x dx plus the integral a, b of 5 dx. Yeah, so we know that this integral is equal to k. Remember, well, there's a couple ways you can do this. One way is if you know that you have a constant and you know the property, you can just say that's 5b minus a. Okay, another way you can do it is, if you don't want to do it that way, you can do k, right, plus, and then you can integrate 5 and then do this thing that they do in class, right? So you put the upper and the lower bound, and then you'd see that it ends up being 5b minus a. Both ways work, okay? One you can do the shortcut, one you can do the actual antiderivative. So this is another type of u substitution question you might get asked. Let's do part C. Part C here, when we take the derivative with respect to both sides, we get du dx is equal to 5. So then du is equal to 5 dx, or dx is equal to du over 5. Okay, so if we go ahead and plug in everything for our u substitution, we have f of u dx is equal to du over 5. And then let's plug in our bounds into our x's to see what the new bounds are. And magically, right, b over 5 times 5 is still b over a. So then what's the only difference here? We have this 1/5. So our answer for part C is 1/5 times k. So that's the analytical way of evaluating areas when you don't really have numbers. So I'll even leave my notes for you, but I'm gonna let you try some on your own. So get out your thinking caps. I'm gonna launch a poll. See if you can calculate some of these. These ones you should get actual numbers too. I'll even be nice and solve dz for you if that helps you for any of these. I'll give you a couple more seconds to keep working before I start explaining. So for part A, right, if we start plugging in our bounds, we get the same bounds. And usually I think that's what you should be expecting, right? You should be expecting similar bounds. You plug in the u, you get f of u. When you plug in for dz, you get du over 3. So then the area should be 1/3 the area of f along those similar bounds. So the answer to part A is just 4/3, right? You get 1/3 the area. What about part B? If we plug in our bounds into this one, when we plug in 2, we get 3. And then when we plug in 1/2, we get 6, right? So we're gonna need to flip it. So I'm gonna flip it and make the sign negative. So it's negative the area of 3 to 6. When I plug in u, I get u. When I plug in dz, I get dz over -2. I can factor out that -2. So part B should have 1/2 the area of my original graph, right? So that one is equal to 2. And then for part C, what are we going to do here? We're going to plug in our boundaries again. When we plug in 7, we get 6. When we plug in 4, we get 3, right? It's the same bounds. Imagine that. And then we plug in our u, right? So it's f of u. And then since we have an addition inside our integral, we can split it up into 2 separate integrals. Integral to 3 of 6 of 5. This one can be in terms of dz. This one will be in terms of du, right? This one is just the area 4, right? And then when we have this one, it's 5. And when we take the integral of 5, it's just the difference of the bounds. So this one's 4 plus 15 is equal to 19. 4/3 to 19. Any questions there? So this one's fair game, right? They're probably going to award you points for knowing to do u substitution. They're probably going to award you points for knowing to change the bounds. Don't forget to change your bounds. They're probably going to award you points for solving for the dz or dx or whatever you're solving for. And then they'll probably give you a point for the actual numerical value. Somewhere in there, I think they can get 3 points. I think this might be a 3-point question. All right, so then finally, we're going to take these and we're going to combine all these concepts into specific APFRQs. All right, so this one was from the 2019 exam. So what do they give you here? They say this continuous function is defined along this closed interval -6 to 5. And the figure above shows a portion of the graph consisting of 2 line segments and a quarter circle centered around the point 5, -3. So here's the center of my circle. And then here would be the radius, right? If that's the center of the circle. So the radius would equal 3. The figure above shows, it is known that the point 3, 3 minus rad 5 is also on the graph of F. So part A says if the area from -6 to 5 is equal to 7, find the value of -6 to -2. Show the work that leads to your answer. So we're going to evoke that thing that we talked about. We need to find the value of -6 to 2. And what's the tricky part? The tricky part is the values of 6 and -2 are over here and they're not even on the graph. But we can use that property where we add it to the area from 2 to 5. Right? And by doing that, we should get the area of -6 to +5. So let's go ahead and calculate the area then, right? So we need to pay attention to what we have above the curve. So here's a triangle of dimensions 1 by 1, right? So this is a positive 1/2. What do we have over here? We have a negative area, right? So that's a triangle of dimensions 2 by 1. So that area is -1. That's not 2. I'm such a liar. The base of that triangle is actually 1.5. Isn't that awful? That's 1.5 by 1. So 1/2, 1.5 by 1 is -3/4. Gross. Then what do we have? We have this triangle here that has a base of 1.5 by 3. What's 1/2? 1.5 by 3, that's positive 2.25. And finally, what else do we have? We need this area underneath this, right? That's like under the circle, but that's like part of a square. How the heck do we do that? Well, we take the area of the square, right? And then we minus the quarter circle. So this area is going to be, the square is 3 by 3 minus the area of the quarter circle, which is pi r squared over 4. So this area right here should equal 9 minus 9 pi over 4. Isn't that lovely? So let's start stacking together our area for this thing then, right? So this thing is equal to 1/2 minus 3/4 plus 2.25, which is 9/4, plus 9 minus 9 pi over 4. Imagine if they had given to you under the curve and then they like messed everybody up because they didn't do a negative sign. So if we simplify that, that should equal 9 pi over 4. Let me see if I have the answer. Negative 9 pi over 4. 3/4 minus 1/2 is 2/4. I thought I had the answer written down here. $11? Am I right? 11? I hope I'm right. Yeah, it's 11 minus 9 pi over 4. And then when we have this area over here that we don't know, -6 to -2 of f of x dx, plus this is equal to, and the question tells us is equal to 7, right? So then if we solve by isolating, -6 to -2 f of x dx is equal to 7 minus 11 is -4. Add the 9 pi over, it's 9 pi over 4. This is a fair game question, right? You don't need a calculator. In fact, a calculator probably mess you up on this question. You have to do a lot of critical thinking there. And it's something that you could also type in, right? You can't type in the integral on the left-hand side, but you can definitely type in your numerical answer. Any questions on part 1? Let me, can I cut and paste this? Well, let's do part 2 then. It says evaluate the integral from 3 to 5 of 2f prime of x plus 4. See if I can copy this. I put it down here. Perfect. So we can use the fundamental theorem of calculus here, right? So let's split it up a little bit. If we want to split it up, it'd be 2 integral of 3 to 5 of f prime of x dx plus integral from 3 to 5 of 4 dx, right? And what's the fundamental theorem of calculus part 1 say? If we're taking the integral of f prime of x, that should equal f of 5 minus f of 3. And then if we know this part, right, this part we've done a few times now, it's 4 times 5 minus 3. And then what is f of 5? Well, f of 5 is just 0, right? We're given the graph of f. And then what's f of 3? F of 3, they gave you that weird point, right? F of 3 is equal to this weird point right there. So then it's 2 times 0 minus here. You got to pay attention to your grouping, right? 3 minus root 5 plus 4 times 2 is 8. And then if you want, just leave your answer like that, because then you'll get full credit. Otherwise, if you forget to distribute your negative sign, you're going to miss out. Cool, so we've evoked 2 parts of calculus, right? We've done the area under the curve definition. We've done the fundamental theorem of calculus definition. Part C, it says the function is given by, g is given by that, the integral from -2 to x of f of t dt. Find the absolute maximum, right? And what's the easiest way to do absolute maximum? We're gonna do a table. So if you were to see this on your test, make sure you also write this out. G prime of x is equal to f of x. If we take the derivative of both sides, we know that the derivative of g is just going to equal f. And on so many of the FRQs that I've seen, they literally just give you a point for writing that, even if you don't know how to do anything else. So write g prime of x is equal to f of x. Now, how do we find the absolute absolute maximum? We need to set our derivative equal to 0 to find our critical values. So we need to find where f of g prime of x is equal to 0 or f of x is equal to 0 for critical values, right? And do not forget that it could also be undefined, except here we don't have any points where f is undefined. So where do we get our critical values? We get our critical values at -1, 1/2, and 5. So x is equal to -1, 1/2, and 5. And so let's start doing our number line test, right? Or not our number line test, our t-table. So we're going to test not only our critical values, right, but we need to test our endpoints. So we need to test -2 and +5 as well, right? So -2, -1, 1/2, and 5. So 4 values to test. Well, let's start here. Well, -2, right? If we look at g of x is just the integral from -2 to -2. So if we just plug in -2, right, that integral is just equal to 0. And then what? For the next one, we were trying to find the integral from -2 to -1. Well, what's that? That's just the area of this triangle right there. Right, so that value is just 1/2. And then what about 1/2? If we're going to plug that in, it's the area from -2 to +1/2. We found that the area of this triangle under here was -3/4, right? So we got +1/2 minus 3/4. That's equal to -1/4. And then from part A, I'm just going to steal the answer from part A. The value when we plug in 5 is 11 minus 9 pi over 4. And if you plug that in your calculator, it's going to be negative, I think. So then this would be justification. And then you could say something like, oh, no, it's not. Haha. This is a big number. Let's see. I have my calculator here, so I'm not cheating. 11 minus 9 pi over 4. 3.93. I'm way off. So the max value occurs when x equals 5 because, and then you can say g of 5 is equal to 11 minus 9 pi over 4. And that would get you full credit. I got a question that says, why do you plug in the x values into the integral instead of f of x? So remember here that f of x is the derivative. So you plug in answers into your derivative when you're doing a number line test. And a number line test tells you like the increasing, decreasing, increasing, right? That's useful for relative minimums or relative maximums. When you're doing an absolute maximum or absolute minimum, you want to do a t-table and you want to plug in values into your normal function, not your derivative. So keep that straight, right? If you want to do a number line test, you will plug in your critical values into your derivative. If you want to do an absolute test, you're going to plug in the numbers into the regular function. That's a really, really good question there. Any other questions about this one? Okay, uno más. Another accumulation question. So this one's obviously, this is question 1. This one's a calculator active. We're gonna pretend like the calculator is not active. So how would you answer A using a sentence? I think you could easily answer A with a sentence without giving me a number. Can y'all write the process of how you would answer A? Good. For part A, all you need to do is take the integral from 0 to 8 of r of t dt. Right? And the key phrase here is during the time interval, right? It's during the time interval. You don't need to add whatever was there in the beginning. Right? So that's how you do part A. Just take the integral from 0 to 8, write down a nice sentence and call it a day. Now, B says, is the amount of water in the pipe increasing or decreasing at a time of t equals 3? Now, they obviously can't ask you that question on the test. How would you describe a process to solve it, though? Maybe they'll say, how would you solve part B if you had a calculator? So go ahead and type in the chat box how you would solve part B without giving me a number. So notice in the question, they give you R as a rate function, right? So this is a rate function, the rate at which rainwater flows. So this is already the derivative function, right? And then what about D? D is also a rate function about the water draining out. So first things first, we need to set up this. This would be your overall rate. So R of T minus D of T, right? We have the positive rate that's flowing in, so we leave R of T positive. And then we minus D of T because that's the water leaving the tank. Now, when are we going to have water increasing? We're going to have water increasing when the inflow is bigger than the outflow, right? So we either need R of T minus D of T greater than 0, or you can say when R of T is greater than D of T, because these are the rate functions. So when somebody responded, they said, take the derivative of these functions. And you don't want to because they're already rates. They already represent the derivative. So to answer this question without actually doing the work, you just need to say, we need to see if R of 3 is greater than D of 3. If R of 3 is greater than D of 3, then it is increasing. Right? If R of 3 is less than D of 3, then the rate of water is decreasing. Sorry, I said the rate of water. I should have said the amount of water. The amount of water is decreasing. Take a look at part C. Part C says, at which time between 0 and 8 is the amount of water in the pipe at a minimum? Justify your answer. Can y'all write the process of how you would answer this question without giving me actual numbers? How would you answer part C? So I think this question is kind of tricky because there's two rates going on. So the actual rate function should be this R of T minus D of T, right? That's the net rate of change for part C. So we have, this would be the total rate of what's going on in our tank. And then what happens? If we want to find the total value, we need to integrate that function. So this would be the amount accumulated from 0 to T. And since we're not supposed to use the same letters, I'm going to change the letters on the inside of the function to, I don't know, X maybe. So this expression represents the amount of water accumulated. So then what do we need to do to solve for this one? We actually need to find the critical values of this thing. So it's not just of R. Why wouldn't you add 30? You can add 30 to this function, right? Because this is the amount accumulated, but the total, right, plus 30 would equal the total water. And it doesn't matter which one you use because we're trying to find the critical values. Right, so we find the critical values by taking the derivative of this function. So then we take the derivative, so we set r of t minus d of t equal to 0, right? These would be your critical values. When we take the derivative, the 30 goes away, right? So find critical values here. And then from there, since we're trying to find an absolute minimum, right? Notice the wording here is implying absolute minimum. Then we want to do a t-chart, right? So we're going to test our bounds. Our bounds were 0 and 8, right? And then we have our critical values in here. And then are we going to plug it into our derivative? Or are we going to plug it into our integral? We actually need to plug it into our total water function. So plug in to the total water function. Any questions on that? So to reiterate, right, we have the r of t minus d of t. That's the net rate. Then we take the integral. That gives us the total amount accumulated. We take the derivative to find the critical values. Once we find the critical values, we go plug all those values into our amount function. And then for those of you who want the actual numbers to use in this, I'll post the answers in the Dropbox so you can look at the actual numbers. I just want you to get an understanding of how you do it conceptually speaking. So for those of you who are curious, the next class is going to be on Monday. And so what y'all can do over this weekend is I'm going to go ahead and send out FRQs that have been modeled based off of everything that we've discussed so far. So anything from units 1 through unit 6. And then if you'd like to submit your answers either by typing or by taking a picture and responding to the email that I send you, responding to the email that I send to you, I'll go ahead and be able to grade them and give you feedback. That's entirely up to you. I know some of you have a lot of work to do, but I do think that it's really important that you practice either typing out your answers or writing out your answers and taking a picture of them. Cool. Alrighty, if you don't have any questions, that's it then.